In this fourth module of Chapter 9, Module 9.4, I will present graphics designed to visualize the concepts involving mark recapture, with special emphasis on showing how life years in a mark recapture study can be disaggregated into two groups. One, the individuals living that are never captured, and two, the individuals that are captured. But in this latter group, the life years in this group can be further subdivided into the times from birth to last capture and the time from last capture to death. Consider four individuals, A, B, C, and D, that lived 2, 5, 8, and 10 years, respectively, for a total of 25 life years lived by these four individuals. Now suppose we capture A, C, and D at these different ages depicted by circles, but not B. We arrange these in a new graph ordered from top to bottom according to the capture age for A, C, and D, and we insert the lifeline of B at the top. Now let's compute the disaggregated life years. We see that the 5 years from B not captured and confirmed alive for A, D, and C at ages 1, 5, and 6 years respectively. Finally, we see that there are 1, 5, and 2 years lived post-capture before these individuals died, totaling 8 post-capture years for the grand total of 25 life years lived in these different categories. This schematic captures the essence of the challenges with estimating survival and longevity from mark recapture data. Not all individuals are captured, and virtually no individuals are captured at or shortly before death. Now let's take a look at slightly more realistic results for a simulated hypothetical butterfly mark recapture study. We have age on the x-axis and number of individuals on the y-axis, with each individual depicted by a horizontal line, the length of which is proportional to its lifespan, and these are ordered from shortest to longest, top to bottom. Ages at capture are indicated with the black tick marks. There are 1,000 individuals with a daily capture probability of 10%. The actual survival of these 1,000 individuals is shown with this red dotted line, with a total of 44,200 life days lived. This means that the average individual of the 1,000 marked individuals lived 44.2 days. The data are arranged from top to bottom, shortest to longest duration from release until last capture. There are 35,809 life days under this curve, with a total of 4,391 marks. There were 63 individuals that were never captured before they died, for a total of 830 life days lived for non-captures. This means that there were 937 individuals captured and released, which lived a total of 7,615 post-capture life days. If we look at just the survival schedule for the baseline and compare that with the recapture survival curve, where the duration from release to last capture are ordered from shortest to longest from top to bottom, we see that there is a substantial difference because of the post-capture life days lived. We can adjust the survival curve based on the last capture by first estimating the capture probability. Once we know this probability, we can estimate the interval between captures, which in turn can serve as a rough estimate for the number of days lived after the last capture. This is not a perfect adjustment, since the interval between captures is related to, but usually greater than, the interval between last capture and death. Of course, we know the capture probability is 10% because we built that into our model. But suppose we did not know that probability, we can compute as follows. The capture probability equals the number of marks minus the number of last captures, which equals 1,000 minus the non-captures. This is all divided by the number of capture days. We plug in the numbers and we get 0.0965. If this is the probability of recapture, then the inverse of this is the average number of days between captures, which is 10.4 days. We add this number of days to every capture, and we see that the adjusted recapture survival curve is much closer than the survival curve based on last capture. But notice something interesting here also, which gives additional insight into the mark recapture data. The individuals with the shortest time from birth to last capture have the longest post-capture period, and therefore the estimate underestimates survivorship, as we see in the upper left graph. In contrast, the individuals with the longest duration from birth to last capture have the shortest post-capture life days. Therefore, as we see in the upper left, the correction over-adjusts the adjusted survival curve. This ends this module 9.4. I hope that you gained new insights into mark recapture survival estimation from these attempts at visualizing the concepts inherent to the method.